Well, hey, chemistry students. This is Mr. Bornheimer, and I'm coming to you today from my classroom, where I am going to talk about orbital notation. Okay, so this is just a little bit different than what we've been talking about in class, and it's not going to take super long to kind of go through some of the steps and whatnot. In doing this. This is kind of like the last thing we're going to do with electron configurations, and then you'll basically be ready for your test. So let's go ahead and get started. Let's look at the simple electron configuration for carbon. Okay, so we're going to start with carbon. And if you were to look at your handy-dandy periodic table, so, here it is. We would see that carbon is element number 6. And because it's element number 6, it has 6 electrons. Okay, so that's going to become important here as well. So 6 electrons, that's what we're dealing with. And I'm just going to go ahead and put that there. And that's going to be a focus for this particular lesson. Now, a couple things we're going to also have to do. We're going to want to write its electron configuration, and we're going to want to do the electron configuration right from the beginning. So not the noble gas configuration or the abbreviated configuration as it's called, but we actually want to go ahead and use the full electron configuration. Now for carbon, it's not such a big deal because there's only 6 electrons. So let's go ahead and do that. And if we have our periodic table, we see that carbon is in the 2p part of the periodic table. So we're going to go 1s2, 2s2, 2p, and then we need 2 more electrons to make 6. So we're going to go 2p2. Okay? And now what we're going to do is we're going to go ahead and we're going to draw this out like if we were actually filling the real orbitals. Recall, orbitals can only hold 2 electrons. All right, so a couple things about orbitals, first of all. Every time we see a box, we're going to call that an orbital. Okay, so this is kind of like a key. And if we see an arrow going up, we're going to call that an electron with a clockwise spin. And when we see down arrows, we're going to call those electrons with counterclockwise spins. Okay, so I'm going to highlight the things that are important here. The box, an arrow going up, and an arrow going down. These are going to become important for us. Okay, so the next thing that you need to know about orbital diagrams is that every sublevel has a different number of orbitals. All right, so you have S sublevels, which only have 1 orbital. And you have P sublevels, and there are 3 different orientations, or 3 individual orbitals. So P actually gets what we call 3 boxes, okay, because it has 3 orbitals. D, okay, gets 5. Okay, because it can hold, it has 5 different types of orbitals. Okay, and F gets 7. Okay, now inside of each of these orbitals, we can put electrons. Okay, and the way this works is that an electron goes here. That's an electron with a clockwise spin. And in order for this orbital to fill up, it has to have 2 electrons, okay? That's an important idea here. So 2 electrons must be inside each orbital. Now, if you have 1 electron spinning in one direction, there's a rule, and we're going to talk about it a little bit more in detail later, but there's a rule that says you have to have electrons that spin in another direction, or opposite, counterclockwise. So we're going to go ahead and denote it like that. So this right here, what you're looking at, this would be considered a full orbital. It's got 2 electrons inside of it, 1 clockwise, 1 counterclockwise, and it is considered 1 full orbital. Okay, so this is kind of what we're doing. We're kind of drawing a representation of electron configurations. And the reason we draw it out is because there's a couple rules that really only can be conveyed in this way. Okay, so this is why we're doing this. Now, if we have p orbitals, okay, these are all our p orbitals, they each can hold 2 electrons. All right, so if I start putting 1 in here, that would be p1. But now it gets kind of interesting. You see, electrons want to kind of delve into each orbital before they fill up all of the orbitals. What I mean by that is that in a particular sublevel, like this p sublevel, each orbital will obtain 1 electron spinning in the same direction before it can obtain a second electron spinning in the opposite direction. Okay? Now, this is what I like to call the firsts before seconds rule. And the reason I like to call that is if you've ever been someplace where you have a big group of people that are eating, you always want to wait until everyone has gone through and gotten their food first, if you're polite that is, before you go back and get a second. So the way this works in the electron orbitals, okay, is an electrons, as they fill up a particular sublevel, they will put 1, or they will fill up with 1 electron in each orbital before they go back and put a second electron in each orbital. Okay? I'm going to reiterate this again, but I want you to see it over and over and over again. Okay? And finally, the F, okay? You would put an arrow here. Oh, Mr. Bornheimer's bad. You can't do that. You got to put 1 in each box first before you can put 1 in the second box. Okay, now there is a reason for this. A half-filled orbital is more stable than an empty orbital. Okay, so if I were looking at a single orbital, okay, or I was looking at a p sublevel, you could look at it like this, and this would be correct. There are going to be times when you might want to do this, okay, but this would be incorrect because you don't have an electron in here and you've already filled this one up. The reason that this doesn't happen naturally is because when you have a situation where you have at least 1 electron in each orbital, that creates a more stable environment. Down here, you might have, let's say, this first orbital filled up, but you have an empty one here, which creates overall a greater instability. And atoms, their whole purpose is to become more stable. Okay? That's why they react. That's why they bond. That's why we look at the electrons, because it's this big game of becoming stable versus unstable. Okay, so that's what we're trying to do. So let's go back to our example of carbon, okay, and let's draw the orbital notation for carbon. Okay, let's do this. So every time I see an S, okay, like here, I'm going to put a single box. So I see an S, I see an S, and I see a P. And every time I see a P, I'm going to put 3 boxes. Okay? So this would have a total of 1, 2, 3, 4, 5 different orbitals. Okay? An S, and 3 P's as options. Now we go through and fill them up using the electrons, the 6 electrons that we have. So I'm going to start right here with the 1s orbital. And I'm going to go 1s1, 1s2, and now this one's done. Notice I'm filling up each sublevel, then moving on. Okay, so in this particular case, because there's only 1 orbital in an s sublevel, I only have to fill up 1 box, and then that particular sublevel is done. So now I move on to 2s, and again, the s's are all by themselves, so I go 1, 2, and now I have 2s2. So now I've accounted for 4 of my electrons. Okay, and now we get to the 2p's. And we say, what do I do here? I have 2 electrons left. When it comes to a sublevel that has 3 or more orbitals, we have to follow that first before seconds rule. So we go 1, and then we go 2. And now I've used all the available electrons. So for now, I'm done. So when we zoom out, this, what you see here, okay, this is going to be the orbital notation for carbon. 1s, 2, okay, so 1s, 2, 2s, 2, 2p, 2, and that's what carbon looks like. All right, now let me go ahead and show you kind of what some of these other orbital notations look like. And I have an example in one of the PowerPoints, and you could go online and find this. Okay, so here's this is from PowerPoint number 3, and you can find this on bclassroom.com. But I want to go back just a few slides in here, and I want to look at this table right here. This is the first 10 elements of the periodic table. And what you'll notice is the atomic numbers listed there. And what you'll also notice are all of the orbital diagrams. Okay, so I'm going to kind of zoom in here for a moment. Notice that hydrogen, okay, has 1 electron, so it has 1 arrow going up. Then there's helium, okay, so we have helium here, and there's 2. And then we get to lithium, the 3rd element, and that is the first time that we add a second orbital, okay? Notice that the number of arrows represents the number of electrons in that particular element. Then we go on to 4, so we have 1s, 2, 2s, 2. Then we go to 5. And this is where we start to add p orbitals. And if you look, number 5 is boron, and boron is the first element in the p block. Okay, so boron is right here. And so we went 1s2, 2s2, and now we have boron over here. We're going to 2p. All right, so boron has a 2p electron right there. Okay. Then we go to 6 electrons, and notice now I see that first before second rule coming into play. I see it coming into play here and here. I'm putting 1 electron in each orbital, and I'm going to try to fill up the whole sublevel with 1 before I go back and put in 2. So we see that again here, 1, 2, 3, and now that there's 1 in each box, when we get to element number 8, which is oxygen, we can start putting in our second electron. And then we fill that up. So we go all the way to neon, and then we have, okay, so this is P1, P2, P3, P4, P5, P6. And at the end of 2P6, we have neon, which is a noble gas. Okay, so this is what orbital diagrams look like. Okay, and they fill up. So let's go ahead and take another look, let's take another look at an example here, okay? So let's add a page here. And let's pick some element, let's pick sulfur, okay? So we're gonna go with sulfur. All right, sulfur has 16 electrons. Let's go ahead and write its electron configuration, and then from there we will determine its orbital diagram. Okay, so we go 1s2, 2s2, 2p6, 3s2, and then from there sulfur is at 3p4. Okay, and just to double check, we go 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16. So we have accounted for all of those electrons. All right, so now I do the orbital diagrams, and I'm going to go ahead and draw the boxes. And I'm going to do it right underneath the electron configuration so that we can see the correlation between the configuration in the orbital notation. Okay? So every time I see an S, I put 1 box. Every time I see a P, I put 3 boxes. If I had a D, I'd put 5. If I had an F, I'd put 14. Or, well, 7. Okay? So S, S, okay? Now here's a P, so we're going to need 3 boxes. Then here's an S. Then here's a P. Okay, so here's all the boxes lined up for us to use. Let's go ahead and start filling them in. Okay, with one S2, okay, what I can do is I can say, okay, that is 2 electrons, and they have opposite spins, clockwise, counterclockwise. And then I have 2 S2, so I'm going to put 1, 2. Okay, so now the first sublevel is filled up. Okay, check. Second sublevel filled up. Check. Now 2p6, which means I'm going to put all 6 electrons in here. So I'm going to go 1, 2, 3, first before seconds, 4, 5, 6 with different spin. And now that sublevel is filled up. Check. Then I go to 3s2. And because it is 3s2, it's filled up. Now that sublevel's filled. Check. Moving on. And this one's 3p4. So this is not 3p6, it's 3p4. Therefore, I'm only going to use 4 electrons. So I'm going to go ahead and put 1, 2, 3, first before seconds, and then 4. And I'm done. Okay, so this is what orbital notations look like. Now these rules, first before seconds, opposite spins, they actually correlate to people that came up with these ideas that help us to think about how electrons behave at this subatomic level. Okay, so the names of these people are really, they're not too bad. Okay, so I'm going to go ahead and I'm going to just kind of explain to you who they are. Okay, so anytime you see opposite spins, okay, opposite spins were this idea that was developed because when something is spinning, it creates a force. Okay, so as a matter of fact, I happen to have a giant gyroscope here. Okay, it's a gyroscope, and what you do with this gyroscope, okay, is when you spin it, it creates a force. And this force can be seen here. Okay, this is no trick, it's an actual gyroscope. It creates a force. Now notice if I stop spinning it, it just hangs limp. Okay, so gyroscopes are a great example of what happens when something is spinning. It creates a force. It's very hard to, wow, this is very hard to move side to side because it's fighting you. Spinning objects create forces. That's actually one of the reasons why we have some of the weather patterns we do in the United States and actually all over the globe, because the Earth is spinning and it's creating forces. Okay, so we have these effects. So there was a guy, and his name was Pauli, and Pauli said that there has to be these opposite spins inside an orbital. Okay, so we call this Pauli's exclusion principle. So when you think of opposite spins, think Pauli. Okay? Now, the first before seconds rule, so when you have boxes and you need to put 1 arrow or 1 electron in each orbital before putting in a second, the first before second was actually developed by a guy by the name of Hund. Hund. Okay? Hund. You can think of Hund hungry. Hungry, first before seconds. Everyone's hungry, so they've got to get there first before they get their seconds. Okay? So Hund, hungry, first before seconds. Courtesy. Okay? Pauli, opposite spins. Pauli, want a cracker? Okay. So kind of a crazy bird, crazy opposite spins. All right, so Pauli, spin, Hund, first before seconds. And that's what these guys were kind of responsible for helping us to understand how electrons behave at the subatomic level. The last one, which I've actually already discussed in class, is the fact that electrons will fill up from lower energy levels, all right, kind of like the chocolate fountain effect. And this was by this kind of idea where, you know, electrons kind of fill up energy levels, and then it goes up to the next energy level, then up to the next energy level, okay, so that electrons are filling from the inside out. The guy off bow, or the off bow principle, okay, where electrons fill at the lower energy levels to higher energy levels, okay, lower energy levels to higher energy levels. Okay, this is what we have going on, and this should help you. If you have any questions, please email me or contact me at bclassroom. Feel free to watch this video over again if you have any questions. You can also find lots of resources online to help you with orbital diagrams. They're a very popular idea. But yeah, so if you have any questions, contact me at www.bclassroom.com. I hope you have a wonderful day. Thanks for watching.